In this chapter, we will discuss additional fundamental topics that are vital for the understanding of structural and mechanistic organic chemistry. We will learn how carbon uses all of its 4 valence electrons for chemical bonding by hybridization of its atomic orbitals. We will discuss the state of hybridization of carbon in methane, ethylene, and acetylene. We will discuss the state of hybridization of nitrogen in ammonia and N-methylethanamine and of oxygen in water and formaldehyde. We will learn to predict molecular shapes based on valence shell electron pair repulsion theory. We will learn to define formal charge and how to correctly indicate formal charges on various atoms in a molecule or ion. We will learn the concept of resonance and how to write resonance structures of a molecule. Hybridization of atomic orbitals of carbon in bond formation. The ground state electronic configuration of carbon indicates that it should form only 2 bonds using its 2 valence electrons in the p orbitals, since the electrons in the s orbital are paired. However, carbon is able to use all of its 4 valence electrons for chemical bonding. It forms CC single, CC double, and CC triple bonds, as well as CN single, CN double, and CN triple bonds. It also forms CO single and CO double bonds. To explain the nature of all types of bonds that carbon forms and the bond angles and the shapes of molecules that have these bonds, Linus Pauling proposed the theory of hybridization. Pauling theorizes that carbon promotes one of its 2s electrons to the empty 2p orbital and reorganizes the resulting 4 orbitals in various ways to form different types of chemical bonding. sp3 hybridization of carbon to form methane, CH4. To explain the tetravalency of carbon in methane and the shape of methane, Linus Pauling proposed the theory of hybridization. As per this theory, promotion of an electron from the 2s orbital in carbon to the vacant 2pz orbital and mixing or hybridizing all the 4 orbitals will result in 4 new orbitals of equal energy called sp3 orbitals. These sp3 orbitals are directed towards the 4 corners of a regular tetrahedron. Overlap of the sp3 orbitals with the s orbitals of 4 hydrogens will result in methane. The bond between carbon and hydrogen are called sigma bonds. Electron density in the sigma bond resides between the 2 nuclei. The shape of methane is tetrahedral with the HCH bond angle of 109.5 degrees. Only in this shape there are least possible repulsions between the bonded electrons. The central carbon in methane is referred to as sp3 carbon. sp2 hybridization of carbon to form carbon-carbon double bond in ethylene C2H4. In sp2 hybridization, after promotion, only two p orbitals and one s orbital are mixed or hybridized to create three hybrid orbitals called sp2 orbitals. They are of equal energy and are directed at an angle of 120 degrees to each other in the same plane. The unhybridized p orbitals remain perpendicular to this plane. When the sp2 carbon combines with another sp2 carbon and four hydrogens, ethylene is formed. The sp2 orbitals make all the sigma bonds. The two p orbitals overlap sideways to form the pi bond. The electron density in the pi bond resides above and below the plane of the flat ethylene molecule. sp hybridization of carbon to form carbon-carbon triple bond in acetylene C2H2. In sp hybridization, after promotion, only one p orbital and one s orbital are mixed to create two hybrid orbitals called sp orbitals. They are of equal energy and are directed at an angle of 180 degrees to each other in a linear manner. The two p orbitals remain perpendicular to each other. When two sp carbons and two hydrogens combine, acetylene is formed. The sp orbitals make the sigma bonds and the p orbitals overlap sideways to create the two pi bonds. The pi electrons give a cylindrical symmetry to the molecule. In a triple bond, one bond is always a sigma bond and the other two are pi bonds. sp3 hybridization of nitrogen to form ammonia-NH3. Based on the shape of the ammonia molecule and the H-NH bond angle, an sp3 hybridization was proposed for the nitrogen atom in NH3. In this model, the electrons in the ground state configuration of nitrogen rearrange by hybridization to create four sp3 hybrid orbitals. One of these orbitals contain a pair of electrons and hence unavailable for normal bonding. The above four sp3 orbitals are directed towards the four corners of an irregular tetrahedron. This gives it a pyramidal shape. When three of the above four sp3 orbitals overlap with hydrogen s orbitals, ammonia is formed. The shape of ammonia molecule is pyramidal with H-NH bond angle of 107 degrees. The NH bonds are sigma bonds. The orbital containing a pair of electrons does not participate in normal bonding. sp2 hybridization of nitrogen to form C-N double bond in imines. In sp2 hybridization of nitrogen, only two p orbitals and the s orbital mix or hybridize so as to create three hybrid orbitals called sp2 orbitals. They are directed at an angle of 120 degrees to each other in the same plane. One of these orbitals contain a pair of electrons which are unavailable for bonding. The unhybridized p orbital remains perpendicular to this plane. When one sp2 nitrogen and one sp2 carbon and the appropriate substituents come together, they make N-methylethanamine. The sp2 orbitals makes the sigma bonds, while the p orbitals overlap sideways to make the pi bond. sp3 hybridization of oxygen to form water, H2O. Based on the shape of the water molecule and the HOH bond angle, an sp3 hybridization was proposed for the oxygen atom in water molecule. In this model, the electrons in the ground state configuration of oxygen atom rearrange by hybridization to create four sp3 hybrid orbitals. Two of them contain a pair of electrons and are unavailable for normal bonding. The above four sp3 orbitals are directed towards the four corners of an irregular tetrahedron. When two of the above four sp3 orbitals overlap with hydrogen s orbital, water molecule is formed. The shape of the water molecule is bent with HOH bond angle 104.5 degrees. The OH bonds are sigma bonds. The lone pair electrons requiring more space bends the HOH bond angle in water molecule. sp2 hybridization of oxygen to form CO double bond in formaldehyde, CH2O. In sp2 hybridization of oxygen, two p orbitals and the s orbital mix so as to create three hybrid orbitals called sp2 orbitals. They are of equal energy and are directed at an angle of about 120 degrees to each other in the same plane. Two of the sp2 orbitals contain a pair of electrons and are unavailable for normal bonding. The unhybridized p orbital remains perpendicular to this plane. When one sp2 oxygen and one sp2 carbon and two hydrogens come together, they make formaldehyde. The sp2 orbital makes the sigma bonds, while the p orbitals overlap sideways to make the pi bond.